Okay, so the idea here is that you're going to be producing two different species in your one pot reaction. So say for example you have propanol as your starting material. You're going to get bromopropane and chloropropane as products. And what you're going to get as far as analytical material to try and analyze your ratio of products is an NMR spectra. And we've got two different species, and what we know is that these protons here will both show up as a triplet, and they will be the most deshielded protons in the NMR spectrum. Now, once you get lower down in chemical shift, you're going to see messier peaks because one, the central methylene protons will both show up as a sextet, and there's a good chance that they're going to overlap. So it's going to be pretty messy. And then our final methyl groups, they'll show up as triplets, but again, there's a good chance that they're going to overlap. The ones that are right next to the halogens will be more differentiated. Anyway, um, if you had equal moles of these two compounds in the solution, your NMR spectrum would give you integrals, and they'll typically show up, well, either underneath the chemical shift axis or right above the peaks in the spectrum. Um, and if you have equal amounts of these two molecules, we know that in each case we have two protons in the environment. So if the two of them are present in equal amounts in terms of moles, we would have a 2-to-2 integral ratio. Again, a ratio, right? It could be 1-to-1, 4-to-4, whatever. But they would be the same if we have the same number of moles of bromide and chloride. Now, I'll tell you right now, this is not going to be the case. And so let's start looking at some other options here, just so we can look at how to think about this. If you had a ratio of 4-to-2 for your integrals, and I'll tell you right now, you will be told which peak comes from the bromide and which peak comes from the chloride. So if you have a bromide to chloride ratio of these proton environments of 4-to-2, what this means is that you have twice the number of moles of bromide as you do chloride. That's why you've got uh, protons, 4 protons from the bromide, 2 from the chloride. Um, if you wanted to, you could use any peaks you wanted. If you wanted to, for example, to compare. If you wanted to compare the integral here, where we've got 2 protons of the bromide, with this integral of the chloride, where you've got 3 protons, you could do that. It makes almost no sense to go and do that unless you want to start getting involved with fractions right away. And I know that most people don't like that. Um, not from not from necessarily saying it, but frankly from how horrible people are at manipulating fractions. So stick to protons in the same environment, in a similar environment, but mainly with the same integration if you can. That makes the math much easier. So let's try another example here. Say we have an integral ratio of 15-to-4 bromide to chloride. What does this mean? What is our actual molar ratio? And there's multiple ways you can go about this. One way would be to say, okay, well, I know that if I have 2, if my chlorine integral were 2, then I know I have one molecule of the chloropropane. So how can I change this 15:4 ratio to get it to 2? Well, I just divide everything by 2. So then that means that I've got 7.5 equivalents of bromopropane for every one molecule of chloropropane. If you want to set up, ratios, if you want, you can go about it a variety of ways. But your end result should be the same. And so that's how you're going to take the information from the spectrum, turn it into a ratio, a molar ratio of your bromide and chloride, using then the overall mass that you've got of these materials. Using that information, you've now got to a situation where you're in with the exact same boat as pre-lab question 3, which hopefully you solved on your own. If not, hopefully you at least understand it. And if so, you should be out of the lab in no time. If not, well, good luck.